Hello students, welcome back. Today we'll be working on Notes 27, and this is where we're going to be using linear, quadratic, and exponentials to model relationships for our data. So last class we just did linear. We used Desmos regressions, and today we're going to expand that to quadratic and exponential, so you can see the graphs that those would be like. So we'll use the same procedure, but we want to choose the best model. So I have a table shown here, and it's actually at the left, and it has the degree that a batter is hitting the ball at, and the distance in feet that the ball travels. And so the first thing we'll do is enter that data into Desmos. Now, if you've forgotten, you hit the plus sign and then the table to get the table. But since I already had entered the data, I'm just going to go ahead and let us use this. Remember, if you can't see your graph, you can hit the magnifying glass to fit the data, and it will put the data on the graph for you. Then, because this looks like a curve, it's not a line, and so this looks like something that is hitting a maximum and then going back down. That would be a quadratic. So going back to your notes, for a quadratic curve, we want to type in this as our expression. So remember, we don't use the equal sign, we use the little tilde, which is up in the top left corner of your keyboard. So I'm going to go back to Desmos, and remember, you have to hit add expression, and then we will type in y1. It will put it as a subscript, then the little tilde, and then ax1, and we're going to square that, and then plus bx1, and then plus c. And so you see that the quadratic regression gives us a curve that opens down for this. So your data, let me move this out of the way. You have your A, B, and C, and we have an R squared. We'll have to talk about what we'll need to see from that. So going back to your notes, the first thing that it asks us is, what is the model function? Well, we decided to use a quadratic. Once we got it graphed, we saw that it should be a quadratic. And then you're asked about the correlation coefficient. Now, that is generally going to be the value of R. And when you do a quadratic regression, it doesn't give you R, but you can make that calculation because it would be the square root of R squared. So we just need to do the square root. So use your square root button and type in the value that you have for R squared, which would be 0.9812. And so that gives us a value of 0.99055. So this second 5 is going to round this up to a 6, so 0.9906. So going back to the notes, we'll fill in R equals 0.99, I think it was 06. I'm going to look at that again. Yes, 9906. All right, and then it asks us for our model equation. So this is the quadratic. So if you if you want, you could go ahead and write down y equals, and then you'll want to leave space for the a, but put your x squared. And so let's go look up what the a is. And a is negative 0.173714. So we'll fill that in, negative 0.173714. And then we'll look at B. It's 14.5212. So we'll add on 14.5212 and then put our x. Remember that after B comes the x. And then finally, you'll have your C term, which is in this case negative 21.8977. So negative 21.8977. And so that is the model equation that we will use as we answer our questions. So this question is, what distance will correspond to an angle of 5 degrees? So notice that your degrees were your x's. So we can substitute in to the model equation for the x's. So that would be y equals, and then we have negative 0.173714. And then for your x, this is an x value, we'll put in 5, and that gets squared. Then plus the middle, so 14.5212. Substitute in your 5 for the x, and then minus 21.8977. And so we can go to the Desmos calculator and do that calculation. So starting off with your a, negative 0.173714, multiply that by 5 squared, and then add to that 14.5212. Do this again. And multiply that by 5. And then subtract your C term, 21.8977. And so this is 46.36. And so to make that match the other data, we'll round it to the nearest tenth. So 46.4. And that will be the distance traveled. So y would equal 46.4, and this is measured in feet. This is the y value. So this is the distance that the ball would travel at an angle of 5 degrees. Then this one's asking you what angle or angles would correspond to a distance of 270 feet. Now, I'm going to show you this one in a couple of ways. So this is a y value, and so we can substitute it in for y into our equation. So 270 equals, and then we'd have negative 0.173714 x squared, and then plus 14.5212 x, and minus 21.8977. But what we would have to do with this is, since this is a quadratic, we would have to get our equation equal to 0, and then we would have to do the quadratic formula. So we could do the quadratic formula, but we could also use the graph to answer this question. So we're going to go back to Desmos and take a look at the graph. What we're looking for are where your y values are at 270. So notice that I am traveling here on the graph, and I'm going to stop when I get to 270, or as close as I can get to 270. I'm not sure I can get right on it. That's close enough. So 33.7 at 270.18 feet. So remember that it said to give one or both, and this is one of them because there's going to be one on the other side. So 33.7 degrees. So using the graph, x would equal 33.7 degrees, or x could equal, and then let's find it again. So going, and actually this said to hang on before I do this, this said to go to the nearest degree. So we would actually need to round that to 34 degrees. All right, and I accidentally erased just a little bit of that. Put that back. All right. So let's see if we can find that other x, going back to Desmos and getting on the other side of the maximum. So again, I'm looking for 270, and that's close right there, 270.159, and we have 49.9 as our angle, which then when we round it to the nearest degree is going to round to 50. So I'll put that 49.9, and then we're going to round that up to 50 degrees. So those are the two angles where you'll get a distance of 270 feet. So if you wanted to, you could do the algebra and use the quadratic formula, or you can look it up on the graph, which is a lot easier. And then the second question said the first baseman is positioned 100 feet from home plate, and the right fielder is positioned 180 feet from home plate. The batter wants to hit the ball halfway between these two players. What angle to the nearest degree should be used to accomplish this hit? So you have to do a little interpretation here, because you need to know what halfway between 180 and 100 is. So you could do the math on that by taking 180 plus 100 and dividing that by 2. So that's going to give you 280 divided by 2, which is going to be 140. Or you could just think about what that would be. All right, so this is actually a similar question to what we had before. What would x be for the y to be 140? So in other words, 140 will equal then our equation, and we could use the graph to solve that for x. So I'll go ahead and write my equation, and then we'll go back to the graph. or you could do the quadratic formula if you really wanted to. All right, so I would prefer to go ahead and use the graph. So we're looking for 140 for the y value. All right, so I'm going to kind of use my scale here, and I actually hit pretty close right at the beginning. So 140.506, and I don't think I can get any closer than that. So it says that we have an angle of 13.3. We'll see how they tell us to the nearest degree. So we have an x of 13.3 degrees, and so that would round to 13 degrees. And we can take a look at that angle, or it happens again on this side. So we want to be at 140. And so as we zero in on that, we see that 70.3 would be the other angle that happens at. So 70.3 would be close to 140, and that'll be our other x value. Remember, with the quadratic formula that you get two x values. So 70.3, which would round to 70 degrees. So there's your first example. It was a quadratic, and you have the advantage of having a calculator that will do all that difficult math for you. All right, and so then our second example is about a bacteria that's been determined that if a human is infected with a population of, and that actually is 1 billion of these bacteria, that he or she would die from the infection. And so they know that a person will likely come into contact with 500 bacteria at the initial point of infection. And basically, they want to know how quickly would it grow to this 1 billion level, so that they could administer medicine or take actions to prevent that from happening. So again, you would go to Desmos and type in the data. I've already done this. Remember, you hit the plus sign, choose the table, enter in your data. So I've already done that. I can't see my data, so I'm going to hit this magnifying glass to see it. Now, when I look at that, it is curving up. It is not a line. A line would go straight. This is curving up. It's also not quadratic because it's not hitting a maximum and then coming back down. So as we look at our options, this one is more like the exponential graph. So for the model function, we're going to choose the exponential. And so then we're going to go up here to the top and look to see, this is what we want our exponential graph to be typed in as. So y1, the tilde AB, x1. All right, so let's go to Desmos, hit add, go to expression, type in y1, and then shift and the tilde, A, B, and then use your shift 6 to get your exponent, x1. So we scroll on up here. You can see that we have an r squared of 1. So remember that r squared is not exactly what we want. We want a value for r. Now, hopefully you know that the square root of 1 is 1, but if you've forgotten, you can do the square root like we did on the first one. Whoops, I don't want to add that there. Okay, I may have to retype that. I'm going to go ahead and retype this. Okay, then hit enter. And here I was trying to do your square root of 1, which is just 1. So your r squared is 1 on this. That means it is a perfect fit. So the graph completely predicts what is going on with this. So your model equation is going to be y equals, we're going to go back and get our numbers off of Desmos. The A is 497.928. So I'm going to do that one first. So 497.928. And then this is times B. So I'm going to use a parentheses for that. And let's find our B value, which is positive 1.18255. So our B value, 1.18255. And make that one a little bit better. Then we'll close the parentheses, and x is our exponent. So this is our model equation. And this question, we have one question: when would the bacteria population grow to this deadly level of 1 billion if left untreated? So that 1 billion is your number of bacteria. So we're going to put that in for the y value. So that's got 9 zeros to it, and then equaling the rest of your equation. And this is not something that we have, or this actually is something that we've worked on solving. So let's go ahead and do the math on this. So what you would do is, didn't draw that line very well. We would divide both sides. Let's try to draw that line again. By the A. So we'll divide by 497.928 on both sides. And so we'll use Desmos to help us out with that. We can actually erase this. 1 billion divided by our A value. And so that gives us this number, 2008322. I'm going to write that much down. All right, so And then there are some decimals. I'm going to go ahead and write down all those decimals. 48839 equals, and then this is gone. We have 1.18255 to the x power. All right, now to solve for that, we would have x equals, we would use a log with a base of 1.18255 of this giant number. All right, and so we can do this again using Desmos. So I'm going to go ahead and hit enter, go to functions, miscellaneous, log base A. So your base was the B 1.18255, and it was this number that we were doing the log of, so 2,000 or 2 008,322. That's actually 2,008,322.48839. And so 86.5, let's look and see what kind of units that is. 86.5, these are measured in hours. So that's actually kind of amazing. 86.5 hours. That is, if you think about a 24-hour day, that is less than 4 days that it would take to grow to that deadly level. So there's an example of how you might have to do your math. You actually could have found this, although it might not have been as easy because that is such a high number, because right here you're only at 6,160. So you'd really have to climb the graph to find that 1 billion number, which is why using the algebra on this was a little bit easier to find your 86.5 hours. All right, so I did not do a linear model since you had a whole assignment on that, but these are your 3 options after you graph your data. You're going to look at your data. This one was clearly a quadratic. This one was exponential. So you're going to look and see what's the best fit and then choose that. And from there, use one of these 3 setups to do the regression and answer your question. Good luck with your homework.